Vou dar agora. Já estamos ao vivo.
Bom dia a todos os presentes. Vamos dar início à cerimônia curta, breve, de abertura do Encontro Nacional de Física de Partículas e Campos. Estamos aqui na presença da presidente da Sociedade Brasileira de Física, professora Débora Menezes, e do comitê organizador do evento. Então, sem ter exatamente um protocolo de abertura, vamos passar a palavra à nossa presidente, né? Eu creio que talvez, eu não sei como é que foi feito a abertura dos outros eventos, né? Mas eu acho que talvez tenhamos que falar inglês devido à presença de alguns, mas acho que ficam totalmente à vontade aí, né, no protocolo. Professora, a senhora quer que eu fale primeiro, ou a senhora fala primeiro? Como é que funciona?
Como quiser.
Como quiser? Então, por favor, a palavra é sua, né? Gostaria de dar boas-vindas a todos, né? Esse é um evento da SBF, que está sendo organizado após o interstício de 2 anos, né? Então, por favor, professora.
Okay, so I will start speaking in Portuguese because I didn't expect to talk about a larger community. So I just think about some important things for Brazilians, and then I will just speak for two or 3 minutes, and then I switch to English again, okay? So, bom, a gente está vivendo tempos bem difíceis, né? Eu fiz uma listinha aqui de coisas que a SBF está fazendo. E nesses tempos, por isso que eu vou falar em português, porque acho que isso interessa mais para a comunidade brasileira, né? Mas a gente está aí no meio de uma pandemia, a gente está com falta de verba para educação, a gente tem problemas nesse momento com a CAPES, sem saber exatamente como avaliar o que é que está acontecendo, qual a origem dessa denúncia para o Ministério Público, né? Se é que houve uma denúncia. Fora esse negacionismo científico orquestrado pelo governo, que acaba sendo amplificado aí pela falta de letramento científico dos brasileiros, enfim, momentos complicados. Então, e justamente por causa dessa pandemia e da gente ter que realizar esses eventos remotos aí pela SBF, o Manuel Messias disse que o ano passado nem houve, né, o encontro de partículas e campos. A SBF abandonou 54 anos de experiência e teve que começar do zero, né, nesses novos moldes. Então, para que isso fosse possível, o empenho dos coordenadores dos eventos foi fundamental, e, é claro, todo esse apoio aí dos funcionários da SBF, que a gente tem que agradecer, que também tiveram que se redescobrir para viabilizar eventos como esse, né? Então, eu agradeço todo mundo antecipadamente pelo sucesso, porque eu tenho certeza que vai ser o evento, porque todos os outros foram um sucesso. Então, claro que não é o ideal, mas é o melhor que a gente pode fazer e tem dado muito certo. Eu queria só aproveitar esse momento para falar algumas coisas que a SBF faz e que eu acho que não chega, não é do conhecimento de todo mundo, né? Organiza o mestrado nacional profissional, voltado para os professores do ensino médio, coordena o exame unificado de física, que é necessário para o ingresso na maioria dos programas de pós, disponibiliza um repositório de aulas virtuais para o ensino médio superior, completamente gratuitas, estão lá na nossa página. Então, se as pessoas que estão me ouvindo aqui gravaram aulas, também estão convidadas a contribuir, é só mandar o link das aulas para a gente, que a gente tem uma comissão que dá uma olhadinha e disponibiliza essas aulas. A SBF é responsável pela coordenação das Olimpíadas Brasileiras de Física, Olimpíadas Brasileiras de Física de Escola Pública, todas as Olimpíadas Internacionais de Física. Publica revistas científicas, né, de qualidade, a Revista Brasileira de Ensino de Física, que é Qualis 1, né, não sei agora como é que vai ficar nessa confusão, a Brazilian Journal of Physics, a Revista de Física Aplicada e Instrumentação, a Física na Escola. coordeno Física ao Vivo, que vai ao ar cada 15 dias, sempre às quartas-feiras, às 7 da noite. E a gente está atuando agora para a criação dos conselhos federal e regionais de física, que são necessários para regulamentar a profissão, que foi reconhecida só em 2018. A gente coordena um site de verificação de notícias, o Verifísica, que agora está em parceria com o CREF, que é um programa bem conhecido da Federal do Rio Grande do Sul. Organiza um monte de seminários, né, webinários agora, disponíveis ali para todo mundo, e apoia uma série de eventos científicos, inclusive esse, e outorga vários prêmios que vão, pelo menos 3 deles vão ser abertos agora ao longo dessa ou da próxima semana. Bom, apesar disso tudo que eu falei, né, a minha percepção é que pouco disso chega ao alcance de todos os sócios, então a gente vai fazer um esforço especial aí ao longo dos próximos meses para melhorar a nossa comunicação com sócios e potenciais sócios. Bom, por enquanto era isso que eu queria falar. So I wish everyone a very nice week. I hope you have good webinars and fruitful discussions, and well, have a nice work. That's it. Thank you.
Thank you very much for the nice words, Professor Débora Menezes. So I will say some words in the name of the organizing committee to the people that is here now. So good morning again to all the people here. We'd like to greet the president of the Brazilian Physics Society, Professor Débora Menezes, that spoke to us. I'd like to greet the president of the Particles and Field Commission, Professor Jailson Alcanis, that is also here, and all the members of the commission, of the organized committee. I'd like to greet the invited speakers, the people from the foreign countries and from the Brazil. I'd like to greet the professors, doctors, students, and all the Brazilian particle and field community. I'd like to greet everybody, the people from SPF that made this meeting possible. Let me say, it is with great satisfaction that we are gathered today to start the 41st edition of the Brazilian National Meet of Particles and Fields, which brings together the Brazilian community of particle physics, quantum field theory, gravitation, and cosmology. This edition should have taken place in 2020, but it was canceled due to the COVID-19 pandemic, which unfortunately devastated the world in Brazil in the last 18 months. After a frozen interstice of 2 years, today we meet again remotely to hold this national meet with the kind participation of foreign speakers, Brazilian speakers, and the authors registered. It is also our moral obligation to remember the losses. About 4.7 million fatal victims in the world, in the almost 600,000 lives of Brazilian people claimed by the pandemic. Brazil was hit so hard. Despite having only 3% of the world's population, the country accumulated 13 of the world's total deaths. These numbers represent the chaos that has marked the daily life of Brazil in recent 2 years. However, it is necessary to move forward, taking the message of education and science into all parts of this big country, which has active physics groups from the south to the north of its vast territory. Today, we celebrate the continuum of life due to the science and the strength of Brazilian physics. In this sense, we are grateful to the Brazilian Physics Society, to the speakers, to the chairs, all the participants who actually make this meeting to happen. Overcome the moments of adversity and open space to the hope and to the lights of science and knowledge, the organizing committee is delighted to declare open the activities of the 41st National Meet of Particles in Fields edition 2021. Thanks everybody for the presence and participation. Okay. So now we'd like to continue to begin the first section of the meet. In this case, I call the Professor Jair Salcanis to introduce the Professor Tamara Davis to the first section of the day.
Okay, can you hear, Manel?
Yes, I'm here.
Okay, so good morning, everyone. Good evening, Professor Tamara Davis, who is in Australia. She is our first speaker. So I'd like to welcome again everyone to this 2021 National Meeting of the Brazilian Physical Society, the Division of Particles and Fields. And it's a great pleasure for me to introduce our first speaker, Professor Tamara Davis, who is Professor of Physics in the School of Mathematics and Physics at the University of Queensland, Australia. Professor Tamara is an expert on the physics of the cosmic acceleration, and she has made very important contributions to the field of cosmology, especially on the studies of the dark energy, and which is the mechanism behind the current cosmic acceleration. Tamara has been involved as a member in some of the most successful international collaborations in the field of cosmology, such as the WIGGLE-Z survey, the Dark Energy Survey, the INDESI. For her work in cosmology, she has been awarded with some prestigious medals and awards, like, for example, the Medal of the Astronomical Society of Australia for early career research impact, among many others. So I'm pretty sure that she's the right person to tell us and to teach us this morning about astrophysical constraints on fundamental physics, which is the title of her presentation. So Tamara, again, thank you very much for having accepted our invitation. It's a great pleasure to have you here this morning, Brazil, evening in Australia, and I pass the word to you.
Thanks so much for that very kind introduction, and thanks so much to everybody for having me and to the organizers for inviting me along to come and speak today. It really is an honor to come and give this talk for the Brazilian Society. I am, it's always disappointing that we can't visit in person, but I'm really glad that I did actually get to visit Brazil at the very end of 2018 when we had a Dark Energy Survey collaboration meeting there. And so it was great to be able to come in person and see that my colleagues in the Dark Energy Survey and some of the physics that's going on there in Brazil. So let me share my screen. And there we go. So yes, I'm going to give a talk today on some of the astrophysical constraints on fundamental physics. And I mean, one of the reasons that I get excited about astrophysics is because of the power of the natural experiments that go on up in space that can help us understand the physics here on Earth better. Because, despite our attempts to build like massive colliders and the fanciest experiments that we can here on Earth, we still are never going to actually compete with the power that we see in a supernova, or the extreme gravity that we have in a black hole, or the time scales that we get to see when we can watch the evolution of the universe over billions of years. So as we begin here in Australia, it's a tradition to acknowledge the traditional owners of the lands from which I speak today, the Turrbal and Yagara nations from the Aboriginal people, and pay my respects to the elders past, present and future. Now, one of the things I love about Aboriginal astronomy here in Australia is that some of the constellations that they talk about and describe in their traditions come from the dark patches in the sky, as opposed to the bright patches, the stars, that are from the traditions that I grew up with. And particularly as someone who studies the dark side of the universe, studies the dark energy and dark matter and stuff, that really resonates for me. And I loved that different way of thinking about things. And you in Brazil would also appreciate the beautiful Milky Way that we have in the Southern Hemisphere, as the orientation of the Earth is such that the Milky Way is even more bright from the Southern Hemisphere, because we're looking towards the center of the galaxy, as opposed to the Northern Hemisphere, which is looking a bit more towards the outskirts. So why is astrophysics a good way to understand fundamental physics? It's really the power of the amazing observations that we have at the moment, which is just spurring this enormous amount of interest and discoveries from astrophysics. So you'll recognize on the left here the sort of classic image of the cosmic microwave background from the Planck satellite. So we're able to now actually observe the light from close after that Big Bang. On the right is a much less common image, but this is actually a part of the dark energy survey, where these thin pencil beams, each dot along one of those pencil beams is a galaxy that we measured the redshift of. And the sparkles that you see going off there are the locations of supernovae that we discovered with the dark energy survey. This little sort of animation of it was made by my PhD student, Sam Hinton. And the part of the distance that you see along these bars, about where it gets a bit fainter, that's about half the age of the universe ago. So we're looking back just halfway along those beams is about the light has been traveling for about 7 billion years. And it always blows my mind to think that we're genuinely able to see and understand things with light that was emitted before the Earth had even formed. The power of our observations is such that now we can see things like this. On the left is the map of dark matter in purple that was made using weak lensing, using the dark energy survey. And of course, the extremely cool observations that have been happening over the last 6-ish years of gravitational waves. So with all of this wealth of information coming from outside, from astrophysics, what are some of the questions that we're interested in answering? Well, it's very simply, how did the universe begin? How do the laws of physics work? How will the universe end? Just the small ones. But in slightly more detail, you might want to ask what initiated the Big Bang? How are the initial conditions of the universe generated? Is general relativity the correct theory of gravity, including how we implement it? And can cosmology point us towards a deeper theory of physics, perhaps a quantum theory of gravity? That's one of the reasons I find dark energy so exciting, that maybe it really is pointing us in the direction that our theories need to go to understand our next biggest theory of physics. So yes, how do gravity and the quantum interact? Are there any particles beyond our standard model of particle physics? That's something that we are able to address now, and I'll talk a little bit about constraining the mass of the neutrino and the number of relativistic species in the universe using cosmological observations. And of course, the big question of what are these components of the universe that we think are out there because we see them by their gravitational influence, but they don't appear to interact electromagnetically. So what are dark energy and dark matter? Of course, if we're trying to predict the future, always a challenging task, we need to know what sort of values do the parameters in our cosmological or in our physical models take, everything from the constants of nature through to what the matter density of the universe is, etc. So in this talk, I was going to cover sort of the concordance model of cosmology, talk about how the fact that many observations agree, I need to add an extra end bracket there. Is cosmology finished? No, there's a lot more yet to do. Spoiler alert. look at different types of cosmological probes and sort of basically talk about the wealth of different types of information that we can now use to understand cosmology. And noting importantly that it's not just observations that will get us to further deeper understanding, we also need theoretical advances, obviously. So we need advances on multiple fronts. Okay, if you have any questions during my talk, I'm happy to answer questions along the way as well. If I've not done something, explained something clearly, or if something's you're really curious about something, please just type it into the chat and I'll attempt to notice. And if the organizers can let me know if any questions pop up that I haven't noticed, then that would be great. Cool. Okay, so this is sort of a classic image. This was made for when we were doing the Wiggles Dark Energy Survey, which was a large-scale structure survey of the universe evolving from the quite smooth and homogeneous time in the early universe, from this part that we can see with the cosmic microwave background, becoming more clustered under the influence of gravity and the competing effects of pressure to form the sort of filaments of structure that we see in the universe and the pattern of galaxies that we see today. Now, we use basically measurements from all sides here. So from the nucleosynthesis in the very early universe, how the balance of hydrogen and helium in the universe was made, and some of the very light elements there and in stars, to the sound horizon scale, the distance that sound could travel from the beginning of the universe to the point of last scattering, which has left its imprint not just on the cosmic microwave background, but also on the distribution of galaxies at the present day, which we can look at using the power spectrum of fluctuations. We then look at also things like the luminosity distances that we get from supernovae, and now also from the standard sirens that we have from gravitational waves. The angular diameter distances and the sort of measurements of h, the expansion rate of the universe at different distances that you can get from baryon acoustic oscillations, the gravitational lensing of light, the growth of structure, both statistically and as in the form of peculiar velocities, the motion of things in the universe. And when you put all of these things together, or at least some of them, here's just an example of recent results from a cosmology paper. This one's from Planck 2018, where on many of the cosmological parameters that we care about, we as sort of cosmologists now have the audacity to claim that we know these parameters to better than 1% precision. So when I was in undergrad, which was now admittedly 20 years ago, the people used to heckle cosmology, and that the fact that it was a field that, you know, an order of magnitude was close enough, or a factor, you were pretty good if you're getting within a factor of 2. We're now, that era is long behind us. We're now talking about things with something more like 1% precision. But does that mean if we've got a great successful cosmological model that's made up of primarily 70%-ish of the universe being in dark energy, about 25%-ish being in dark matter. The rest, there's this stuff that appears on the periodic table, or the particles in our standard model of particle physics, light, etc. So are we actually done? Is that all we need to know? Well, I would argue definitely no. For one thing, if you use different cosmological models to constrain the parameters, you get different answers and much larger error bars. So if you extend your model such that, for example, you use different relativistic species of particles, you let dark energy be time varying, these kinds of things, then you get different values for the parameters, and the error bars can go up. We've also started to see some tensions in the data. The error bars are getting so small that we now see some different measurements of the same parameters disagreeing. And we need to know whether that's a systematic error in our observations, which is well and truly possible, or it's an indication of some fundamental physics. We have a great history of being pointed towards cool new fundamental physics by hints of tension. But where do we, what is actually going on here? And that's still unknown. So these plots here were from the Planck 2018 paper, and these look at the sum of neutrino masses and the a current expansion rate of the universe, H0, and the number of effective neutrino species, as well as sigma 8, which I'll talk about, which relates to how clustered matter is in the universe. And these are just showing how the values of these would change as you have these extensions to your standard cosmological model, in which the number of effective neutrinos of relativistic species is fixed, etc. On the left is an example of the constraints that you get where you have the equation of state of dark energy varying. And on the right, it shows an interesting tension where the low multiple poles, so the large scales, are in slight tension with the high multiples, which is the small scales of the cosmic microwave background from the Planck satellite. And so these are all things that we need to explain. And if you're asking the question, is cosmology done? You have to obviously answer the question of not just, how does the universe behave, but why? So we want to find the theoretical explanations that are behind the parts that we don't understand. Okay, great. So let's go dive into the different types of cosmological tests that we can use right now. And I classify them in two main groups. There's the homogeneous ones that test basically the expansion of the universe, and the inhomogeneous ones which measure growth of structure. So the homogeneous ones are things like supernovae or baryon acoustic oscillations, like standard candles and standard rulers, where you're looking at geometric stuff that tells you the expansion rate and how that's changed over time, and that kind of thing. The inhomogeneous ones are how do things clump within that overall expansion of the universe, and what can we learn from the rate of infall into those clumps, how light bends around the clumps, and that kind of thing. So if you're looking just at the homogeneous stuff, the standard candles and rulers are our sort of go-to measurements. Standard candles, as I've mentioned, we've got supernovae. Here's a nice, pretty example of that, and gravitational waves. I've put the fact that here a very famous tension at the moment is the H0 tension, which I forgot to mention on this slide here. The H0 that you measure from things like the cosmic microwave background is a bit below 70, so something on the order of 68, whereas this yellow stripe is the prediction or the measurement that you get from the SHOES measurement of, which is a particular survey of H0 using type 1a supernovae and a distance ladder built up from nearby. And this purple contour here, which is sort of the combined constraints of those, doesn't match particularly well with SHOES, which is has an answer closer up around 73. So that's one of the tensions that we have to try and explain at the moment. The standard rulers include anything where you know the angular size of something intrinsically. So by measuring how big it appears, you can tell how big it is on the sky, how far it is away, rather. And so this includes something like the cosmic microwave background and the baryon acoustic oscillations. And these use luminosity and angular diameter distances as measures correspondingly. You also have some interesting things like time delays of gravitational lenses, which also work a bit more like angular diameter distances. I won't go through this maths right now, but those are some of the ways that we can geometrically measure the distances in the universe. Now, I've mentioned supernovae and gravitational waves a lot. So what's the sort of differences and advantages and disadvantages? Well, supernovae were used to discover the dark energy. I could go into the fact that there are definitely hints that dark energy existed well and truly before the supernovae sort of confirmed it at the end of the 90s. But they're the real sort of clinching. They're sort of a stalwart of cosmology. On the left here is an image from the Dark Energy Survey. I've got a bit of a bias towards using images from DES because that's the survey that I've been involved in. So Oh, I see someone asked that you couldn't see what the different colors represented on the previous image, the one with the shoes and CMB. Here, the different colors here, the blue was the low multiple poles, the red was the high multipoles, and the polarization curve included, and lensing included the green ones. And so the combined contours of the one you want to look at is the combined contours of the temperature and polarization curve, which is the purple one here, compared to the orange band that goes across, which is the supernova constraints. Thanks for the question. Going forwards, sorry. Oh, yeah, so on the left, if you zoom in, so you start with the big image in the back, you zoom in a little bit, and you might see this beautiful galaxy like this. What a supernova actually looks like going off is that little dot that has appeared. If I flick between them, you can see the dot appearing there. On the right is the kilonova observation that's associated with a gravitational wave. So if you look at this, it looks quite similar. You'll see just around here, if you can see my mouse, if I flick back and forth, a dot appears here. That's the kilonova that it was associated with a merger of two neutron stars that was seen in a gravitational wave. Now, both supernovae and gravitational waves can be used as standard candles. In the case of gravitational waves, they're called standard sirens, but really they're just, you use the frequency and the rate of change of frequency of the gravitational wave to calibrate how intrinsically bright the source was. And once you know how intrinsically bright the source was, you can, in terms of gravitational waves, that gives you the distance. And the thing that you're missing is a redshift, because it's the redshift and distance combination that gives you your constraint on cosmology. And so finding a kilonova, or an optical or electromagnetic counterpart to the gravitational wave, is a really powerful way of actually using that to measure distances. It has an advantage over supernovae in a couple of ways. One, that the gravitational wave, not the light, but the gravitational wave itself, only diminishes as a factor of 1 on r, 1 on the distance, as opposed to 1 on r squared, which is the usual, diminishing law that you get for the strength of a source. And so that means we can actually see the gravitational waves. Once our detectors get powerful, it doesn't diminish as much with distance as a electromagnetic source. And so that's really exciting for us to be able to observe the next most distant sources. And I put this slide here because some of the predictions for what the next generation, or sort of next or coming generations of gravitational observatories could detect, is that they could potentially detect every black hole merger in the observable universe, which is just phenomenal for the power that could have. Now, but most of them won't have electromagnetic counterparts, so I'll get to that in a sec. The other advantage, though, is that we know the distances. The calibration comes basically from general relativity theory, whereas the distances to something like supernovae is built up with a distance ladder. You calibrate geometrically nearby to Cepheid variables or Mira variables or surface brightness fluctuations or the many different distance measures nearby. And then you step that, you find supernovae in some of those galaxies, and then you use that to calibrate out to further and further distances. And so it's a multiple step where there can be systematics coming in each step. And I've worked in supernova for almost 20 years now. And this ladder has been built very, very carefully. People have worked really, really hard at this, but it's a really hard thing to do. So it's very refreshing to have the option of using something like a gravitational wave, which skips all of that calibration and just you know how bright it is from theory. If you can just measure its frequency and rate of change of frequency. So that's really exciting. But of course, you don't have the redshift for most of the gravitational waves. And so this means that there's two types of gravitational wave standard sirens that you can use. The first are the bright sirens, where you do see something like I was just showing before, where you have an afterglow from some sort of electromagnetic counterpart. That lets you identify the host galaxy and get the redshift. Whereas the other ones you have are the dark sirens. But the dark sirens are ones where you don't see any electromagnetic counterpart, just as you would expect if you've got two black holes colliding, for example. And those dark sirens are actually still very useful for cosmology. If you have something like this, this is an example of a very well localized gravitational wave from the LIGO-Virgo collaboration. And so this is the localization region. And we can actually look at the distribution of all galaxies in this region, weighted by their likelihood of being in that region and the likelihood of being at particular distances that we get from the gravitational wave, and statistically measure the distances to that. So you basically get a statistical redshift of the average of all of the possible host galaxies. That seems like a really big uncertain thing that sounds a bit crazy that you could actually use that. But these days we're so familiar with making maps of the distribution of galaxies in the universe that doing this statistically with many observations is actually seems perfectly reasonable to us cosmologist people. So here's an example measurement, again from Des, where this is the probability of H naught, and the grey one is the measurement that was made from a single bright standard siren, and this red curve is the measurement that was made from a single black hole merger. Now, okay, this red curve has ridiculously large error bars right now. You can't really measure anything with that at the moment, but because black hole mergers are going to be much more common than the bright sirens, statistically, this is going to be a very useful measurement in the future. You just have to average over many of these and make sure you're unbiased in your galaxy distributions. Oh yes, and motions of the galaxies are important to take into account as well. And this is a little paper that my postdoc Cullen wrote on that topic. Okay, so yes, keep questions coming if you have any. The next sort of most powerful individual probe, at least until recently, for sure, is the cosmic microwave background. Now, it acts as a standard ruler, but it also can be, you got a heap of information from the power spectrum of the cosmic microwave background. Here is a plot of the power spectrum where you've got the strength of fluctuations as a function of separation. This is large multipoles up here. On the right can correspond to the small scales, and small multipoles correspond to large scales because this is in Fourier space. And this beautiful complicated pattern has the amount of dark matter and dark energy that's been seen in like rotating galaxies and the supernova measurements and stuff. And it just all works beautifully. Now, the blue points are the data points. They do have error bars, but for most of the data points, the error bars are just too small to see. You can see a couple up here. And it's just it is really phenomenal if you think about it, that we can use the standard sort of physics that works for sound waves here in the room and gravity, and be able to predict what the pattern of fluctuations would be in this fluid of the very early universe. And this is super sensitive to the dark components of the universe. So if I take this and I change no other part of the model except dark energy, remove the dark energy from this model, this is what the power spectrum would look like approximately, but I've just superimposed on the top here. And if I took dark matter out of the model, that's how it changes. So it's just a hugely sensitive probe to things like dark matter and dark energy. Now, importantly, I've done the very bare bones thing here of removing a component completely. If I do remove dark energy or dark matter, you can tweak other parameters to get a closer fit than this, but I'm just using this to demonstrate how big an effect they do have on the prediction that you get for the cosmic microwave background, which is one of the reasons it's such a powerful probe. Now, what is going on? Where did the patterns come from? Here is an example of if you have a density fluctuation in the early universe, the dark matter we think is pressureless, so it doesn't respond in a sound wave, but the baryonic matter does. It propagates out in a sound wave until the universe becomes dilute enough that sound can't travel anymore. And this is near the era of recombination, when the electrons are able to bond to protons for the first time in the universe without getting immediately dissociated by a photon. And the pattern that this leaves behind in the density distribution of the universe ends up imprinted in the pattern of galaxies that we see at the present day. And so it's this density distribution that we go and we measure using a power spectrum or a correlation function. This is an example of how we make a correlation function of galaxies. We basically pick a galaxy and measure the distance to all of its neighbors and make a histogram. So because there was this sort of preferred separation in the early universe, which was the distance that light could travel from, sound could travel from the beginning of the universe to the surface of last scattering, or shortly thereafter, actually, it was the drag epoch, a little bit after that. There's this sort of preferred distance where you've got these overdensities at this particular separation, and that shows up in the distribution of galaxies at the moment as the BAO peak, so the baryon acoustic oscillation peak. And that separation is can be used as a standard ruler, because once it was imprinted, it hasn't changed, and that distance is large enough that any growth of structural velocities can't have changed the size of that, or the distance to that peak. It can be blurred a bit, but that distance won't significantly change in co-moving space, at least, expanding with the universe. In more detail, this is one of my favorite animations, which has been around for a while now, but I love it, so I'll always show it. This was from Daniel Eisenstein, and this shows the propagation of what happens if you have dark matter, gas, so baryonic matter, photons, neutrinos, all starting out in the universe. So if you come back to the beginning, if you have adiabatic fluctuations, that means that all of a dense spot will have all of the different components dense at the same place. Now, immediately you see that the neutrinos basically just start free streaming out. They interact very little, and so they start spreading out. That has the effect of spreading out the gravitational potential of that initial density fluctuation. You meanwhile see dark matter gets frozen in place. It's dragged a bit by the gravity of the gas and the photons, but it doesn't have pressure support, so it doesn't have a sound wave. Whereas the gas and photons are a coupled fluid at the early part of the universe, and they do propagate as a sound wave. So that as that continues on, you eventually get to the point where these two start to decouple. That's the point where the sound wave gets frozen in. So you can see as that continues, the photons now free stream, just like the neutrinos were earlier. And you end up with this hump, which is stuck at the distance that sound could travel. And this hump at the original location of the overdensity, which is where the dark matter is. And quite soon after that, they each draw gravitationally each other. And so you end up with a situation that looks somewhat like this, with this overdensity bump, which is the thing that we're looking for when we look for baryon acoustic oscillations. So the neutrinos there are important as well, because they carried energy out of the fluctuation, and they would basically destroy small scale fluctuations. And whether the neutrinos are massive or not changes the prediction for how what the exact pattern that we would see here is. And I'll get back to that a little bit later. So here's a picture of some recent paper from the Sloan Digital Sky Survey, which has, actually I should have updated with some of the very latest stuff, but there's some peaks here showing measurements at different redshifts of the baryon acoustic oscillation feature. And I'll talk about this circles in a moment. Okay, so now I've mentioned that supernovae are a standard candle. The cosmic microwave background is a standard ruler, and baryon acoustic oscillations are a ruler that can be applied both radially and tangentially. So if you apply them radially, you get a measurement of the rate of expansion divided by the relative size of the universe, the scale factor at that redshift. And tangentially, you get the angular diameter distance. So I've made them standard basketballs here. You've got basically a standard sphere. Now, the growth of structure can be measured using this because when we measure the distribution for baryon acoustic oscillations, we usually measure redshifts, which is basically measuring the velocity of expansion and using that as a proxy of distance. Using velocity of Hubble constant times distance is you get, speaking very roughly, if you can measure the velocity using the redshift, you can get the distance. So this is how most of the big maps of the distribution of galaxies are made. But of course, if there is motion that is not the expansion of the universe, then that will warp your map. And what we see when we look at baryon acoustic oscillations is we see the distribution compressed along the line of sight in various ways. Because if you have a cluster of galaxies, the galaxies that are close to us will be rushing away from us towards the center of that cluster. So they'll have an additional velocity in addition to the expansion of the universe, and that will make them look further away from us than they would have if they were just moving with the expansion itself. Contrary, on the other side, on the far side, the galaxies are moving towards the cluster, so they're moving towards us, reducing the velocity that they should have had if they were just moving with the expansion of the universe. And that means that around clusters, we see this sort of compression. And that's one of the ways, by looking at how, of course, perpendicular to that, you don't see any compression. So measuring how things are compressed along the line of sight compared to perpendicular to the line of sight can help you measure how the structures are growing. So you measure the velocities going in to structures. And that's a sensitive probe of how gravity works on intermediate scales, which is really interesting because we know that the expansion of the universe is accelerating on the larger scales, but we know that it's attractive, that gravity is attractive on the small scales, like our galaxy. And so where does that transition happen around galaxy clusters? By measuring the growth of structure at a range of different scales, we can measure that kind of thing. And I think I'll skip over the Alcock-Paczynski test, but it's a similar thing using some of the geometry. Now, I've spoken mostly so far about the homogeneous type of tests, but there are some models that can't be used, they can't be distinguished using only distance data. So I wrote a paper in 2007, quite some time ago now, that was using supernova data to test non-standard cosmological models, things that tried to explain dark energy and dark matter. And what was immediately evident was that pretty much every model that I tested that could share the same parameters as our standard lambda cold dark matter model, so the cosmological constant plus cold dark matter model, the best fitting parameters in terms of the expansion of the universe always agreed with the basic lambda CDM model. And those models that couldn't, so you could rule out some models because they were not able to mimic the expansion history. But if they did mimic the expansion history of lambda CDM, then you couldn't distinguish between them using just distance data alone. You had to use some other type of method. And so that's one of the things that got me started moving from supernovae to measure large scale structure. So the kinds of other types of measurements that we do are things like this, where we look for deviations from general relativity by looking for if you, in the metric, you have your time, the prefactor to the time component and the prefactor to the spatial components, and they're the same in general relativity, but they are not the same necessarily. So there are models in which these two differ. Now, the clustering of galaxies is sensitive to the spatial component of this, but lensing is sensitive to both the spatial and the temporal components. And so that can be a way to distinguish models that have these different factors. So that's one of the things that we're trying to constrain. We also want to measure growth. This is often used, the F factor that we use for growth is the logarithmic derivative of overdensities to scale factor. And it's it's closely related to the matter density, but the matter density to some exponent, and that exponent can differ in different cosmological models. So that's another thing that we try and measure. We try and measure the amplitude of density fluctuations. So I mentioned sigma 8 in some of the early slides. It's a bit of an obscure parameter if you're not a cosmologist, but it's pretty easy to understand. Basically, you go out in the universe and you draw a sphere of 8 megaparsecs in radius, and you measure the density there. Then you go and draw another one and measure the density over there. And you do that many, many times, and you measure the dispersion in that measurement. The dispersion in that measurement is sigma 8. And why 8 megaparsecs, you might ask? 8 megaparsecs arises because that is the radius at which the answer is approximately 1, where the density is defined as the overdensity. So the density minus the mean density divided by the mean density. So that is approximately a dispersion of 1 if you have 8 megaparsecs. Now, you'll see this S8 parameter popping up as well, which is a combination of sigma 8 and omega m with this functional form. And the reason that we use that can be seen in, this is an example of a result from the lensing paper from KIDS, which is the kilodegree survey. And if you look at sigma 8 versus omega m, the constraint from weak lensing is this sort of pink contour here. And you can see that it doesn't constrain either sigma 8 or omega m very well, but S8 is basically along the degeneracy line here, or perpendicular to the degeneracy line there. So you can measure S8 quite well. So I see there's a question in the chat, which is can we measure the scale at which gravity switches from attractive to repulsive? And if yes, what methods are employed? Thanks heaps for the question. That is what we're trying to do. And I guess I'm now answering that question of the different methods that we use to do that. It's probably also not going to exactly be a scale. It's going to be a relationship between the scale and the local density. But these different techniques are exactly how we're trying to do that. So thanks for the question. Okay, so in terms of other measurements that we like to do, one is looking at non-Gaussianity. So this can particularly give us information about the initial conditions of the early universe, but then also how things have grown since then. Non-Gaussianity is basically the scale of clusters the same as the scale of voids? Like, do we have symmetry in the density distribution? If there's skewness in that, then it can be non-Gaussian, and if it's primordial non-Gaussianity, the fingerprint of that gives us information about things like inflation and what could have happened at the very early universe. I've already mentioned peculiar velocities. I mentioned measuring them statistically using redshifts and growth of structure. We can also measure them directly if we have a distance and a velocity. We can look at how much that deviates from the expansion velocity at that point, and the rest can be attributed to a peculiar velocity, which is any motion that's not just the expansion of the universe. That also is a really powerful way to constrain the growth of structure. And I was talking about that previous question, what's on what scales are things falling in versus expanding. And so if one of the things we do is look at the redshifts, make a density distribution, and calculate how rapidly things should be falling in based on how overdense different regions of the universe are. And if direct measurements of peculiar velocities don't agree with that, then that will show us that our theory is incomplete and the densities can't explain the infall completely once we've taken into account dark matter and dark energy and different models therein. And then there's really cool stuff like the integrated Sachs-Wolf effect, which is basically if the universe is accelerating with dark energy, for example, the potential wells that a photon falls into when it goes through a galaxy cluster will be at a different level to when the photon climbs out, and you can get an overall blue shift of things of the cosmic microwave background light from behind galaxy clusters. And this is another sort of smoking gun of dark energy, clear indication. Okay, cool. Oh wow, we're almost getting towards the end already. I've been being a little bit verbose. I'll talk about the neutrino mass and number though. So this is, I think when I started doing cosmology, it really didn't occur to me that I was going to be using the large scale structure of distribution of galaxies in the universe to measure the mass of one of potentially the lightest particle in nature, certainly the lightest we know of that's not massless. And how is that done? So as I mentioned before, neutrinos have an impact on the structure that we see. If you have heavy neutrinos, you'll get strong suppression of structure, but over a short range because their peculiar velocities will decay with time. If you have very light neutrinos, you'll get more weak suppression, but over a large range. Now, here is showing the impact on the power spectrum of a completely unrealistic value of the contribution of neutrinos to the energy density of the universe, where this would be making neutrinos all of the dark matter. But this is just to demonstrate the point that it changes where the peak of the power spectrum is and the slope here, and also the strength of the wiggles that you get, the baryon acoustic oscillation wiggles. This is the kind of range that we typically observe, and this is the range that's hard to model because you need to deal with nonlinearities in the theory of the growth of structure. Now, why is this important? One of the things that we want to understand with neutrinos at the moment is whether we have a normal or an inverted hierarchy. So we know from oscillation experiments and from solar experiments, etc., that we know some of the differences between the masses of the neutrinos, but we don't know whether we have two light and one heavy or vice versa. And the cool thing is that, so we've got a lower limit from lab experiments and etc. And now we have an upper limit from cosmology, because if you had more total mass than this, then we would have been able to see it in the power spectrum. And so we're getting really close from cosmology to putting constraints on these hierarchies, because if we're at about 0.13 electron volts at the moment, if we find that the upper limit is lower than that, then we'll be able to rule out the inverted hierarchy. Now, that's a model dependent statement, as I said before. If you have a different cosmological model, you could end up loosening these bounds or getting a different answer if you have time varying dark energy or something like this. So that I do admit that's a model dependent statement, but it can put some really interesting constraints on neutrinos. This is one of the recent constraints from DES, where you can see this 3 by 2 point measurement I'll mention in a second. You can also constrain the number of relativistic species. And this is not just neutrinos. It could be a sterile neutrino, for example, and it could be other relativistic species, because they all would have similar effects. And my favorite, I think this might be my favorite title of a paper. My postdoc, Sine Rima Sorensen, wrote this back in 2013, but it was called What is Half a Neutrino? Because N effective doesn't have to be an integer number, because you can have an effective number of neutrinos that's not integer, because we use that as a way to sort of parameterize the impact. And it's not integer if you have a non-thermal spectrum exactly early in the universe. Okay, So I've only got a couple of minutes left, so I better race through these last couple of things. So some of the really cool measurements are gravitational lensing at the moment. So you get strong lensing when you can get multiple images of the background galaxy formed by light that has followed different paths through space. And these kind of classic images where you've got the red galaxies in the foreground and this blue galaxy repeated in the background, seen from many different angles. And all of these arcs that you see around here. So lensing will typically cause, if you have the high density in the foreground, it will cause things to line up in circles in the background. And you can use that to map the distribution of density in the foreground. So strong lensing is a classic for that, but we can also use weak lensing. And that's when you don't have multiple images of the background sources, but you're taking into account the distribution of many different background galaxies and how they appear with the foregrounds. So that's been done for things like the bullet cluster, which I'll skip over in interest of time, and show some of the really big maps of dark matter that have been made recently. This was an early one from the Dark Energy Survey. This one had 27 million background galaxies. And the shapes of the background allow you to identify the high density regions in red and the low density regions in blue that the light has passed through to get to us. This one is from the Kilodegree Survey, KIDS, a similar sort of pattern. And this one, which I sort of showed at the beginning, is the biggest patch yet. This one is made from weak lensing convergence of over 100 million galaxies. And so the number of galaxies that we can do this with in the background is just astonishing at the moment. And there's a type of measurement that is now, it's going to be much more common now. And so I wanted to just briefly go through what this is, a 3x2 point correlation. So the correlation function I showed for baryon acoustic oscillations before is a 2-point correlation function. 3x2 point is 3 2-point correlations calculated simultaneously. So if you've got background galaxies, foreground clusters, and the lensing of this, you can measure the clustering of galaxies and galaxies, that 2-point. You can measure the galaxies and the lenses and the correlations between those, and you can measure the correlations between the lenses. And that's one of the measurements that's been made lately. And so these are the ones that are giving us some results, which are very constraining, and you can get some similar constraints now using this on parameters like sigma 8 or S8 that are similar in strength to what you can get from Planck from the CMB. So that's a really exciting development. Okay, so I think I'll wrap up at that point with the last thought, which is, if we're going to make progress, then theoretical advances are going to be just as important as observational ones. I've talked a lot about the observational tests at the moment, but we need advances both in fundamental theory, such as quantum gravity, and also our modeling theory. I mentioned briefly the nonlinearities that we have to deal with. And so we have a lot of data that we can't use at the moment because we don't have accurate enough models. So we need advances in many different ways to be able to understand the cosmology. But I hope I've convinced you that there is a lot of fantastic, cool data out there in cosmology at the moment that can constrain fundamental physics. Thanks very much.
Okay, thank you, Tamara, for this excellent and very clear presentation. Thanks a lot. I'm going to open now for questions. If you in the audience want to ask some questions, please indicate, and I open the microphone. Okay, so Luan, just a second. You can open your, okay, it's open now, Luan. Go ahead.
Okay, thank you very much for this presentation. It's really amazing. I'd like to ask about the growth rate, the sigma 8, sorry. How this parameter can determine dark matter and dark energy?
Cool. So the S8 parameter is a really sensitive probe of dark matter and dark energy, because so what we measure is the clustering. So if I go back to the slide where we had sort of sigma 8 here, if we measure the clustering, we know what the initial conditions were at the cosmic microwave background. And so we can put into simulations of the universe and theoretical models how much structures should have grown from that point to the present day. And we can go and see how big the clusters are and what's the density contrast between the most dense clusters and the most underdense voids, not only at the present day, but at every point along the sort of history of the universe, and compare that to our model. And if you have more dark matter, then things will cluster more, because you've got more things, you've got a sort of higher density contrasts to form those structures. So that's why it's a really sensitive probe. And I should mention also that because dark matter was able to cluster much sooner than normal matter, because it was able to cluster before the cosmic microwave background, because it was not pressure supported, it was the seed of structures that formed the big structures that we see today. And without that ability, we wouldn't have been able to grow the largest structures that we have today from the starting point that we can see at the cosmic microwave background.
Okay, thanks, Tamara. Rodrigo von Martins, please go ahead.
Hi, first of all, thank you very much, Professor Tamara Davis, for your seminar. It was very clear and very pedagogical. And I noticed you showed some results from DES, some new results from DES, where it was shown that this S8 tension, probably there's no more S8 tension or something like that. So I would like to ask you what your opinion, I mean, should we still looking for models to try to solve or at least alleviate S8 tension? I mean, do you think S8 tension is still a tension, or do you think in the future we will be able to solve this and it's a matter of systematics or things on this super complex data?
So I think that this very complicated looking plot is probably one of the ones that you're referring to here, where you can see that in the S8 parameter, you've got something like the Planck results are here in green and the dark energy survey results are here in black. And they do overlap at the 2 sigma level there. Their 1 sigma contours sort of just touch each other. So is this a tension? I mean, in particle physics terms, we wouldn't be stressed about this at all. But it's one of those sort of nagging hints. So I am happy to keep judgment aside until we have better data. But I think there's pursuing both the sort of route of finding theoretical explanations that could explain or have the flexibility to explain this type of tension, as well as trying to search for systematics in our data and possibly just getting better data, because it could still be a statistical fluctuation. Those both, I think, parallel routes are important to study at the moment. Of course, I didn't go into the H0 tension in any great detail, but this is one of the classic plots at the moment where the Cepheid variables and the cosmic microwave background differ, but things like the tip of the red giant branch are sort of in between. These should agree with the Cepheids. They're different calibrations at the moment, and so there's uncertainty there over whether this is a systematic error or an indicator of new physics. But you always go and you poke at the bits that aren't quite working right, and you sort of try and see if the cracks stay there or if you find some errors.
Thank you.
So.
Okay. More questions? We have time for more questions. If you have one, please indicate here. Okay, so if not, Tamara, I'm gonna. Well, we have a lot of students in the audience. So I'd like, well, in cosmology, we have many important and very big questions, as you mentioned since the beginning of your talk. So considering the next generation of experiments and cosmological surveys, I'd like to ask you to give your impressions for the students in the audience. If considering this new data, that the upcoming data that we are going to have in the near future, which of these big questions are we going to be able to answer, or to in order to better understand the universe? Which are the hot topics for cosmology, in your opinion? The great opportunities we are going to have to study in the next few years.
Oh, that's a great question, and one that's very difficult to answer. You want me to predict the future? Yes. I ran out of time to mention the other surveys, but since you've asked, I could mention that the types of surveys that are being done, you've got the imaging ones and the spectroscopic ones, you've got wide field, you've got deep, and you've got static, and you've got time domain. And there's interesting, exciting stuff to happen in all of these. I tried to turn these into an actual slide where some of the exciting things that we were going to have coming up from the James Webb Space Telescope, the Vera Rubin Observatory with the Large Synoptic Survey, not the Legacy Survey of Space and Time, etc. This was an incomplete slide because there's just so much stuff that's coming on board, and the next generation of experiments is going to be amazing, because we're really at the point where we're able to measure basically back to the entire observable universe. And where I think gravitational waves are going to be really exciting, because they're the sort of new kid on the block of giving us new types of information that we haven't had before. The square kilometer array and the radio telescopes are going to be amazing in the stuff that they are able to see using the power of those that are being built. And the really challenging one is to find the theoretical explanation, like I mentioned, because we've got so much data so trying to find the theoretical explanations for what we see is really one of the big challenges that's coming up for the next generation, and I guess always for physics.
Okay, thank you. So we are now at 10. It's very late in Australia, right, Tamara? So again, I'd like to thank you very much for having accepted this invitation. I am sure that everybody enjoyed a lot your talk, your presentation. Okay, so we end now this session of this first session of the national meeting. We are going to have a break now and go to the some small communications, right? And those interested in joining us these communications, you can find a link in the site of the event in the SBF website. Tamara, again, thank you very much, and we end the session here. Thank you.
Thanks very much, all.
Okay, bye-bye.